happy to have Peter Engels, who will tell us about his work.
Yeah, thank you. It's a great pleasure for me to be here. I thank the organizers for giving me the opportunity to share some of our results with you today. So the title of my talk is Observation of Barrier-Induced Shocks and Spin Dynamics in Elongated VECs. So my group at Washington State University is actually an experimental group. So I'm an experimentalist, and I'll share some of our results with you. The people who do the experiments in the lab are graduate student Thomas Versal and Maren Mossman. Dr. Sean Mossman is a postdoc. We also had Bandner as a postdoc, who now is in Okinawa, the Okinawa Institute of Science and Technology. And of course, we acknowledge very fruitful collaborations with theorists, and we are always happy to talk to our theorist friends because we learn so much from them. In particular, Michael Forbes. And for the work that I will present you today, we also had very fruitful interactions with applied mathematicians. In particular, Mark Hofer from Boulder, Keith Julian. He's an expert in fluid flow and classical turbulence. And Hannes Kakokidis. And for some spin dynamics, also Chen Wei and this group. And we acknowledge funding from NSF and NASA. So here's a brief outline of my talk, and we can see how far we go down this list. But essentially, I will give you a very brief introduction. But since already at this workshop you've heard so much about quantum hydrodynamics and also VEC systems, my introduction is going to be fairly brief. Then I will present you an experiment where we do a quantum mechanical piston shock. And this will lead us to the question of dispersive versus dissipative dynamics, and dispersive versus dissipative shock waves, and also connections to turbulence in that system, which is turbulence in the channel geometry that we have in these systems. Then we can connect this motion to spin dynamics by introducing spin-orbit couplings. Spin-orbit couplings means we couple the dynamics that we have in the motional degrees of freedom to the spin degrees of freedom in the system. And we can see how we can use these ideas, combine them with this type of experiment, and come out with a unidirectional spin switch that would be interesting, for example, for spintronics applications. And then I'll have a very brief conclusion at the end. So to give you just a very brief introduction, so dilute gas Bose-Einstein condensates, they are a very powerful talk to model phenomena, complicated phenomena from different areas of physics. Prominently, for example, two areas that we are concerned with is condensed matter physics and superphysics, as for example in superfluidity. And for example, in the area of condensed matter physics, we are interested in inducing artificial gauge fields in our system. The atoms that we deal with, they are neutral, but often we want to model systems that have got charge or respond to magnetic fields when they move. And we can do this by engineering artificial gauge fields. Of course, optical lattices are another example, and spin-orbit coupling is also a hot topic in the condensed matter area. In the fluid flow regime, we are interested in quantum hydrodynamics, novel types of solitons, and we've done studies on superfluid counterflow. And together with Michael Forbes, we are also trying to combine these two fields by developing and investigating spin-orbit coupled quantum hydrodynamics. So from an experimentalist point of view, these dilute gas Bose-Einstein condensates, they're a very nice system because they are so well controlled. They are theoretically described by the Gross-Vitolevsky equation over here, and essentially all of these elements that we have in here, we can control very nicely. So for example, these potentials that we have over here, we can actually tailor them using all kinds of devices like digital micromirrors. This is something that Tyler's group has actually perfected. And I think you may have heard about some about that before, or painting potentials. We can play with the interactions in the system by exploiting an atomic physics trick called Feshbach resonances. So we can place our system into different magnetic fields. And based on this, the scattering length that we have in here actually changes. And we've also got tools that allow us to modify the dispersion of the system over here, the kinetic energy term. For example, with the spin-orbit coupling that I have in my talk, we can change the dispersion from a free particle parabola to something that has got a double well shape. Now, from an experimentalist, from a theorist point of view, the system is also interesting because it's nonlinear. So we've got this density dependence in the interactions over here, and whenever things are nonlinear, things become very interesting. So for example, when you've got rotating systems, you get all the vortex dynamics and turbulence that you heard about so much already. These are pictures from vortex dynamics in Bose-Einstein condensates. Those are very early pictures from Eric and Ned's group in 2002, where large vortex lattices were made. Vortex lattice shape deformations were observed from hexagonal to orthorhombic. You can excite surface modes running through a condensate that has got a lot of vortices in them. You can see that on the direction on the surface mode, you can either melt your vortex lattice and get this whole soup of vortices in here, or if you use another quadrupole mode running through your BEC, you can actually push the vortices together into these line features over here. Those are dynamic as the system rotates. If you go to elongated BECs, then the main players, I would say, are actually solitons, which kind of like are the cousins of the solitons of the vortices if you go to just effectively one-dimensional systems where you don't have rotation. And also solitons they come in all sorts of shapes and colors. There are dark solitons, bright solitons, there are dark bright solitons in two-component systems. There are dark solitons, there are dark anti-dark solitons, and of course there are three-component solitons. So there's also a long history in soliton physics, and it's too much work done there to list it out. So I'm just showing you some pictures here from my group at Washington State. What you see over here is two fluids, and these atoms are actually sitting in here. We just pulled them apart for imaging. It's two different spin states, if you like. And this is the dark bright soliton. It's actually a whole train of dark bright solitons, which we created by using superfluid counterflow. Down here, this is what you would call a dark anti-dark soliton, which is different from the dark bright soliton by the fact that the bright component sits on the background. And this is the three-component soliton. Okay. So with this introduction, we now want to use elongated systems and do a quantum piston shock experiment. And this will lead us to considerations of dispersive versus dissipative shocks, and we are going to see that there's also some turbulence in the channel geometry in this system. So what is the basic setup that we have in mind? Well, we take an elongated Bose-Einstein condensate over here, and then we just take a very high repulsive barrier over here. And this barrier we are going to drive through the Bose-Einstein condensate. And so this is going to be our piston, and then we see what happens as the piston is driven through the Bose-Einstein condensate. In practice, this barrier is actually a laser beam that's tuned repulsive on the atoms at 660 nanometers. And the height of this barrier, the barrier strength, is large compared to the chemical potential, like a factor of 10 larger. And then we are going to vary these speeds at which we drive the piston. Typically, we are going to look at speeds that are slightly supersonic or largely supersonic, and then we want to see what's the effect coming out.
And it's wider than the beam.
Yeah. So the beam propagates in this direction, so there is no dependence that the atoms see. It's much wider in this direction as the BEC. And here we have got a finite width of about 11 microns. So it's not really a delta function, but that doesn't matter very much in the subsequent dynamics. And then we can take absorption images from the top. Here's the piston actually driving in. You don't see the piston, you just see the BEC. Or we can make integrated cross-sections, so we just integrate these images up, and these are what you see over here. And you already see something that's quite interesting, or that was to some extent surprising for us. The green curve, that's the experiments, and the blue curve, that's numerics done by Mark Hofer. And it's actually surprising to see that even in these extreme regimes that we study here, extreme in quotation mark, it's not Newton style, not Newton style extreme, but for a VEC, this is pretty brutal, that the GP actually works pretty well.
What is the temperature here?
Essentially, what we study is zero temperature physics. So the thermal component is negligible in the system.
And it is not generated throughout your experiment?
Not on this time scale, no. And the numerics that we also see here, they do not take any thermal component into account. It's just dB. Mm-hmm. So then the question is, what would you expect for this system? So first of all, we all know that there is no dissipation in a superfluid, and so we would expect dispersive, not dissipative dynamics. And for dispersive systems, we know there's the existence of dispersive shock waves, or DSWs. So these DSWs are complex structures. They consist of the following elements. So here I've got a piston that's driven through a BEC. In this case, the piston actually runs towards the right, but in all the experiments that I show you, it'll be running through the left. There's a plateau over here, and then there's a modulated wave train over here. And this modulated wave train has got a soliton front over here, which resembles dark solitons, and a harmonic front over here. And then this theory can actually give us formulas for the speed with which the harmonic front travels and the speed with which the soliton front travels, and they are different. That means as the shock propagates, the whole structure is actually supposed to expand outwards.
Is it one-dimensional?
Yeah, this is one-dimensional. So in experiments, one has actually seen this. So this is from a paper that we published with my paper. And this is not a piston, but it's a collision experiment. So initially we had two small lobes of the BEC with a repulsive barrier. We turn the repulsive barrier off, and the two lobes actually approach each other. And you can see the formation of dark solitons in here, which is connected to two interacting shock fronts. But these dark solitons are connected to these dark soliton trains over here. There have also been related experiments with fermions in John Thomas's group. So one would think that dispersive shock waves, this is what one would also expect for the piston based on the arguments that I have laid out so far.
Can I ask you, PS plus, how it compares to the velocity of sound?
Square root of R. This would be, this is the velocity of sound in this unit. Square root of the density.
PS plus.
Vp is the velocity with which the piston moves. Yeah, and then half Vp plus speed of sound is the speed with which Vs minus moves. And then this guy moves even faster because the shock front is expanding as this thing propagates. Yeah.
May I also ask about the slide before? So when you showed the GPE equation, the theoretical curve. So what potential has been used for that, and what initial conditions?
So this is for a, the potential is nearly harmonic. It's not quite harmonic because we have an elongated dipole trap when we do this. So the initial conditions were a BEC that's relaxed numerically into the shape of our dipole trap. And what was the other question?
No, basically potential and the information.
Yeah.
Okay.
If you're interested in the exact parameters, I can give you them.
You said that your piston's moving faster than the sound speed.
Yeah.
If it moves at twice the sound speed, I think you look like your ES minus becomes smaller then. Or did I misread your equation on the next slide? If VP is twice the square root of rho r, then it equals ES minus. So your piston keeps up with the solid. So does something strange happen if you move at more than twice the speed of sound?
I think the plateau region may disappear then, yeah. Let's see. But so Vp is the piston speed, Vs is the shock speed, and so I take the piston speed and I add the speed of sound to it.
But if Vp was twice the speed of sound,
yeah, then I've got 1 plus the speed of sound.
Vs is always faster than the piston.
I don't think it is. It's always faster than half the piston speed. But if Vp is twice the square root of rho r, then that formula just gives you Vp.
Yeah.
So I guess something else happens when you go faster than twice.
Right. Yeah, maybe I have to look into it, but maybe that the plateau region disappears. Anyways, the plateau is going to saturate at some point anyways, yeah.
No, since the velocity of the dark solid Vs minus, it's smaller than Vp, right? It's smaller, I understand, correct? With time, you accumulate mass in front of the piston, right? So that increases.
Mhm.
Is that true? So, I mean, basically it's like a, I don't know, escalators. There's more and more mass in front of the.
Yeah, but there's a formula for this plateau height too. So this plateau,
So that should be increasing in time, right? It's increasing in time, correct?
I don't think so. I think it's like,
The velocity of the piston is faster than the velocity of the front.
Mhm.
You see, and therefore you should accumulate mass there.
This is steady state solution.
I'm sorry?
I believe this is a steady state solution. We cannot accumulate.
Well, I don't think they have a steady state solution, they have a time dependent solution. So,
yeah, maybe we can look into this afterwards.
okay.
Rho, so the question is rho r. Is that the height of the plateau or the height of the background in that formula?
I think it's the speed of sound in the system, so the background. We can look into the specifics again afterwards.
Okay.
Okay. Yeah.
So is it 3D or quasi?
1D.
1D. And how long did Soliton stay there? How long has they this?
Oh, so this time scale you have here is about 35 milliseconds, so you can expect them to live for about tens of milliseconds afterwards.
So actually, one maybe last question. So, is it correct to say that nodes are associated with the nodes in the pictures?
Second.
Nodes in the
Yeah. So
the heights don't seem to decrease, or it's just hard to see it in the picture.
yeah, it's hard to see, but you can see if you look out here, you have some very fine ripples going out here. This is also a more complicated situation than this one over here, because it's actually two shocks running up. Because it's not just one piston firing through, but two collisions in there. All I'm going to say here is that this is something one would expect. One would expect solitons to emerge, and one would expect to have these trains over here. So now we can go on and ask what one actually sees in the piston shock experiment. So here we've got some pictures from piston shock experiments. Again, this is the absorption picture. And here we've got green is the experiment, and blue is the GP simulation. And we have different times here. The piston is driven through the VEC at a constant velocity over here. This velocity is 2 meters per second, slightly above the speed of sound. And we saw different stages in the evolution as the piston moves through here. And one can see that there are different stages. So first of all, this edge over here, this is just where the piston is as it's driving through the cloud. Over here, on this side, we have got the shock front. Shock front propagating forward as the cloud moves. Oops. Here, we have got a plateau region that has developed. And as the shock actually expands, here, the plateau region gets wider and wider. And finally, when the piston reaches the region where the background BEC has been, the shock, this front over here actually deforms, and it starts forming a rarefaction wave, which is going to have a parabolic shape. Yeah.
Probably very naive and not question, but why is the plateau region actually? Why can you interpret it as turbulent? So what is turbulent exactly? So how do you see this kind of turbulence? It's not momentum space, and it's is there kind of scaling picture behind that, or?
I will come to that point later over here, what we mean by turbulence in this case and what the indications are for the dynamics. That's going to be one of the big punchlines of this talk, actually. So this will be elaborated on a little bit later. Yeah.
Two questions. Do you lose atoms from the trap? Because you can go with the beam all the way to the edge and push them out. So is the number of atoms conserved or not? Or you push them out? So it's not conserved.
It is conserved.
So you don't push them out. So the piston never goes beyond the edge.
Well, the trap that we have is actually very, the trap circuit goes on over here.
Oh, I see. Okay. the second question, why do you say it's surprisingly well? What you would have expected otherwise? You see everything at zero temperature, you don't have equilibration, you see everything is very fast, so it should work, so it shouldn't be surprising. You would be surprised if you wouldn't agree, like I think, but the fact that it agrees is not a surprise.
Well, I can offer you the last. You can go ahead, but I would also like to answer.
Okay, please go ahead.
Well, I think there is one thing that I would respect in thinking about analogy with classical. Shock waves are highly dissipative. In fact, in a classical fluid, and that's something that.
Yeah, but this is not.
I will. So I will perhaps Alfred also could talk about that. But when you have a shock wave, you need to have an entropy increase.
Yep.
Therefore, the only way that you can have entropy increase here is by producing a fluid. Therefore, getting outside the domain of validity of the GP equation. This is for me is an issue that I think we can discuss after. But it's not very obvious to me what do you mean by shock wave. Definitely cannot be the classical shock, unless we have an entropy increase somewhere.
Well,
Why is entropy increase associated only with the normal fluid? I thought entropy increase is just tangling up vortices. Vortices carry the entropy fluid.
No. Entropy increase is something that has to do with determining.
You're just counting states, right? I think you can take a Kangol and contain information in a Kangol. That's just different kinds of information.
Correct.
That's not.
No, that's entropy.
No.
That's entropy. Configurational entropy. You give it as a name.
I think we should go on and we can discuss after. But that is,
I think what they call shock is the front expansive speed of sound. Is it?
So I think, yeah.
Yeah. So that's a shock. That's a shock.
right. Shock wave.
And it has a discontinuity. See, well, I think that's enough.
Yes.
You see, so the velocity is zero in front, you see, but it's different from zero.
Okay,
Basically a sharp transition.
maybe we'll continue in
The region is very narrow. You see, obviously it's not zero. It's very narrow.
I wonder if there's a difference between a classical shock wave and a dispersive shock wave.
Classical shock wave is not dispersive.
Yeah, it's dissipative, right? But in these systems, we would have the DSWs, like dispersive shock waves, rather than the viscous shock waves.
Right, because you mentioned two types of shock waves. So you spoke about dispersive shock waves, and then you mentioned another type.
Viscous shock waves, VSW.
So I think the shock, which was observed by Cornell in 2009, and the one that was observed by Thomas are both dispersive. There is no dissipation there. Even though Thomas initially concluded it was, I mean, he said it was dispersive, dissipative. Actually, that was wrong.
And this again closes the circle to what I said, the GP equation actually fits very well.
Yeah.
Because there is no dissipation in the GP equation.
Yeah.
So based on this, we would expect to have this dispersive shock wave behavior. And so now we can take these images and we can see how well does this dispersive shock wave theory actually fit to what we see. Okay. And so quantitatively, we characterize our features by a couple of measures. One is, of course, the shock speed, this point over here, and how quickly it moves through the cloud. The other one is the width of the shock front from here up to the plateau. And the third one is the plateau height, like how high is the plateau density over here, maybe relative to the background density over here. So in this picture, we are showing experimental results for the shock speed, which is the speed at which this edge here travels forward, for different piston speeds. And so our experimental points are these blue points over here. The GP numerics are the orange points, which are pretty much right on top of it. Now for the viscous shock wave, for the dispersive shock wave, we have seen there are two fronts. There's a harmonic front and a soliton front. Given our experimental parameters, we can calculate our expectations for these velocities, which are the dashed lines shown over here. So quite clearly, they do not fit. if we would use viscous shock wave theory, then we can come up with a line that actually fits the data quite nicely. A little caveat, the data is fit if we use a speed of sound that is slightly lower than what we actually think it is in the system, and I will get back to that point later. So what do I mean by we have to change the speed of sound a little bit? This is the prediction for viscous shock waves for different speeds of sound. If I say I've got a 3D bike system, I've got a speed of sound in the system, which I can calculate. This is the blue curve over here. Then I can say my DC is actually elongated in one direction, so I should average over the transverse profile, which gives me 1 over square root of 2, which is this 1D in quotation mark. 1D speed of sound over here. But we have to go even a little bit below that. And that's borne out not only in the experiment, but also in the numerics. So we keep that in mind. We need an effective speed of sound, but if we do so, then viscous theory fits the data.
So the question is the speed of sound is for the initial test?
Oh, it's, yeah, for the initial density in the center of the cloud where it's mostly uniform. But from the background, yeah.
With a reduced transverse direction, or because of the potential, it's a very narrow transverse direction. Because
of the potential. So our confinement is a tube, if you like. It's harmonic, but it's.
But it's kind of a n cubed, basically. It's a cube.
No, it's parabolic. So
the parabolic, the potential is parabolic.
Yeah. Mm-hmm.
Yes, but the lattice is 3-dimensional. And is it like in every direction the same amount of points, or is it any importance in this direction, or is it only important that there is one long direction, which is longitudinal, and a little bit in transverse direction?
What do you mean by lattice?
You're asking for the simulation?
GP, yes.
Yeah, they were 3D.
It is 3D, okay, which is just anisotropic potential, basically. Because you have transverse direction of the potential and a very wide longitudinal potential. Okay, sorry.
Yeah.
Just to understand if it's purely 1D or 3D reduced to 1. Okay.
Right. So the numerics that marked it were fully 3D.
Yes.
So the next measure is we can look at the plateau height. There's also a formula from viscous shock theory that we can use for the height of the plateau that forms in front of the piston. This is the red line over here, and you can see, yeah, it also fits pretty nicely with the same speed of sound that we used before, the slightly reduced speed of sound. Whereas if we use the one-dimensional speed of sound or the 3D speed of sound, they are off. But anyways, viscous shock wave theory fits. Then we can look at the shock width. As the shock propagates through the BAC, DSW, the dispersive theory, would say that the shock actually expands outwards because there was the harmonic edge and the solid tonic edge, and they run at different speeds. We observe that the shock width actually is roughly the same. This is two different speeds. Blue is 2, and red is 3 millimeters per second, following through the sweep of the BAC, and we don't see any significant change of the width of the shock front. Again, viscous shock theory would predict this thing. When I say that DSW, the dispersive theory, doesn't fit, we also tried fitting the plateau heights, and DSW theory would say the plateaus actually saturate. We don't see the saturation, and this is the shock speed where we would have 2 speeds, and we only see essentially 1 anyways. So the upshot is dispersive theory doesn't seem to describe the data. So the question is, what is going on? And the question is answered by what region you actually are in when you perform these experiments. So over here we have got numerics for low numbers of atoms, that's 10,000. And as the piston moves through the BEC, over here, this is numerics from Mark, we can indeed see these interesting DSW structures form. If you repeat the experiment with much larger atom number, like 400,000 atoms, the piston speed is higher here because the speed of sound is also higher when you've got more atoms in there. So that's not the difference. But then what you can see is that initially you form these DSWs, but then you undergo all kinds of instabilities, snaking instabilities, where these solid tonic features here actually decay and decay into vortices. So in this bulge over here, this is the bulge with the plateau region, you actually do have a lot of vortex dynamics going on.
when you increase the number of atoms, it is because you increase the transversal direction or the length, or do you change there, you see, from one to the other? Because you can contain, you see, cross section to be the same. Does the cross section change?
The trap is going to be the same, but what does change is that now you have to account for radial dynamics.
Absolutely.
The radial dynamics is what comes into play.
So the direct answer to your question is just more particles. Trap is the same.
So the density is different.
Yes.
Yeah, the density is.
So you modify the density. Okay, so that means you see effectively you make the cross section different to see.
Right.
That's also okay. Now I understand.
So the radial dynamics comes now into play, and that radial dynamics allows the solitons to.
You can maintain the same density, and then simply increase it.
Right.
There's two effects here. One is you have more particles, so it gets wider.
Yeah.
But you also have more particles, so the healing lengths get smaller.
Yeah. Okay. Thank you.
Both of those make sense.
So that's naturally that happens. You allow models to develop this way, which you couldn't have that.
Right. Exactly. So we can characterize these two regimes by a number over here that contains the number of atoms, the charge aspect ratio, and the harmonic oscillator strength. And effectively, something like this is going to tell us how important the radial dynamics is going to be in the system. And if we calculate these numbers for what we have over here, we see that here we are at a D parameter that's about 1 or slightly lower than 1, where we would expect the dynamics to be transversely constrained, such that we don't have any radial dynamics going on. Whereas in the system over here, we are at 32, and we now enter the 3D regime. So then we can look closer at this bulge region over here and see what's actually going on there. This is again the numerics, but now they are shown in isosurfaces, so we can actually look inside. And indeed, we do see all kinds of vortex dynamics with vortex lines, vortex bending, vortex swings, these path vortices going over here.
How do you know they're vortex?
Because of the.
What they look like?
Essentially, yes.
Okay.
There seem to be features that have their own tube-like features in the BC that have their own kinds of dynamics.
Take a picture in the other plane to see that this is really one-dimensional. Because you take a picture like this, you see a line. You see, for example, let's see on the right. But if you take a picture, you see from above, you'll probably see a point.
Yeah.
So, but do you have that, or no, you don't?
This is the 3D result, so it exists. Yeah, but I don't have it.
So it's a tomography kind of picture, right?
So these are numeric.
This is numeric.
Oh, it's numeric.
This is numeric.
Yes,
Yeah.
you can tell it as a word.
Okay, so that's sorry.
Yeah, no, this is numeric by Mark.
I didn't read that. It's my mistake.
Yeah, I would be very happy if this were experiments. So experimentally, we do have some indication for this vortex dynamics if we let the cloud just expand very long. And then we can see, for example, images like these. And there you really have to, you need some experience to look at these images to see what you see. But in this case, for example, you've got two holes over here and a little tube going through there, which is indicative of a vortex swing seen from the side, where along these points up here and down here, you actually have got a low density and then a fainter connection from the side. You see solitons actually forming these Y-forks over here, or solitons snaking. So while we can't resolve all the features over here, at least we do have indications for the vortex dynamics that's going on there. And that is my argument why I was calling this turbulent, in the sense that yes, there is a lot of vortex dynamics and connections and stuff going on.
Are there imaging techniques that one can, in principle, use in real time to, transform the numerics to experiment? Is there some absorption or something? Because the density contrast, I guess, is pretty high.
Yeah, it's also a problem of the imaging resolution. In Barengi's group, where they first took a BEC and then they shook it in all kinds of dimensions to excite some turbulence, and then they did expansion images. They were able to see, like with a little bit of goodwill, you could see the vortex lines actually in the BECs. If you want to do this in trap without releasing the BEC, then it's going to be really hard. Like the healing length in our system is about 200 nanometers. And so our imaging light is on the order of 780 nanometers. So that would be really high resolution. So,
but you can let it expand. Maybe you see it.
Yeah. This is when this is taken. These are little snapshots from expansion pictures where we've expanded really far and then just looked at the small region.
These are in situ simulation pictures, though.
Yeah. Right. Okay. So this explains essentially why we have viscous dynamics, because we've got the radial modes and we can put out some energy from the soliton front into turbulent dynamics over here. There is still the question of the effective speed of sound that I haven't clarified. And to put forth an argument for this, one could resort to a technique from the large eddy simulation, where one takes the density average over a little kernel, little cube, because one says, the density in the system is not really uniform. So I should actually modify my density to what I have in the system over here. So if you take a little cube of 5 by 5 by 5 microns, or 5.35 microns over here, and just for comparison, the width of the shock front, like this slope region, was about 15 microns, so this is small compared to this, but it's large compared to the harmonic oscillator length and large compared to the healing length. If you do this, you average the density, and then you calculate a modified speed of sound based on this average density. Then you end up with the frequency of 1.35 millimeters per second, which is the effective speed of sound.
This is what agrees with experiment.
Yeah, this number agrees with experiment.
Then you see the question is that the real velocity of sound creating into a vortex medium like this or not? Is there a theory like this? Because you might have a system like this where you create many vortices, equal and change it, and then you send the sound pulse. Would it propagate to that? You see, because it's not entirely obvious that that would be the case.
I don't know that answer.
Okay, thank you.
What I do know is that we had experiments from Eric Cornell's group where they made large vortex lattices and had sound pulses traveling through the hexagonal lattice. And these experiments showed that the sound front was actually following the hexagonal shape of the vortex structure. So instead of, if you make a large vortex lattice and you just plug it in the middle, you don't see a circle spreading out, but you see it like having the hexagonal shape of the vortex lattice.
This I think there's something different.
Yeah. This was a very
I was just going to comment that we kind of have done this experiment here. Even the lowest frequency, smallest sound wave you can make propagates into that exactly kind of this average over there.
Well, no, but that's an observation.
Yeah,
The question is there a theory which shows that?
I see, right.
You see, because that I don't think is quite trivial. You see to go because you'll have to go to many scales, average your items.
But in principle, you should be able to use the hydrodynamic theory, right? Like you
No, you see,
average it out
that implies that you do an averaging, but it's not a regular type of averaging because you have wide fluctuations in this case.
Right.
So it doesn't look to be obvious.
But that's exactly what we need to do for neutron stars and other things, right?
Well, but the question is there a theory like this? So, right? Okay.
Maybe to come to a last point over here, then there was the question about the rarefaction waves. So the dynamics that I have displayed so far critically hinges on the fact that as the shock pulse propagates, it propagates to a finite background of BEC density. But then as the BEC actually ends comes to the end of the original cloud, there is no finite background density anymore. And that changes the dynamics, because from that point on, there's nothing that would actually set the speed of sound in the medium through which you push the atoms. So what happens then is something which is called a rarefaction wave. And you can look at these waves in the following way. We have got a BEC that originally was occupying this whole space over here. Then very gently and slowly we just pipe the piston in here without creating any excitations. And so at this point, we have got a BEC that's just confined over here in a harmonic trap, and there's no density over here. And then we can just remove this piston, and we can see how does the BEC actually spread out in this direction. Now, theory gives us two predictions. One is the front that we should see is actually parabolic. And this is also borne out in our experiments over here. So the blue stuff is our experiment. We do get in the parabolic form over here. And also we know that the speed with which this shape actually is propagating forward is given by twice the speed of sound. And again, we can see what our system is giving us. Blue is the experiment, green is the numerics. Now we see twice the speed of sound, but this time it's the bulk speed of sound. Whereas previously I had speed of sound divided by square root of 2 to account for the elongated geometry that we have over here. In this case, you see we get a result that's twice the bulk speed of sound. Again, emphasizing that in this, for these parameters, we have got three-dimensional system going on. I think probably with this I should leave it here. And I mean, if I would go to the spin dynamics, it would be a little long. You know, we had some discussions on the way. I can quickly summarize what we see with the spins, or we can just
maybe do a quick summary. It'll be recorded.
Okay, so the next step after this is then to couple spin and motion with degrees of freedom, which is called spin-orbit coupling. And in the experiment, the only difference is that now we add Raman beams, 2 additional laser beams, one from the left, one from the right. We single out 2 hyperfine states of our atom, which we call spin up and spin down respectively. Those are just 2 energy levels in the ground state manifold of our atoms. What the Raman lasers do is they drive transition between the 2 atoms. So an atom can absorb one beam and emit into the other beam and go from here to here. There also is the 3rd state, but we ignore this one, it's out of resonance. So then when an atom goes from one state to the other, it not only flips its spin or pseudo spin, but it also gets a momentum kick because it absorbs from one direction. So it gets an h by k of momentum from one direction, followed by stimulated emission into the other beam, which again gives the atom an h by k kick in the same direction. So as the atom goes from here to here, it gets a 2h by k one way. As the atom goes from here to here, it gets a 2h by k kick the other way. This is the essence of the spin-orbit coupling. If then you ask what's the energy of a system that is coupled by such Raman beams, you would write down a Hamiltonian over here that has got in the off diagonal the coupling between the 2 basis states by the Raman beams. It's just like a Rabi oscillation between 2 states, with the difference that we have got momentum transfer during each Rabi oscillation. This is with e to the 2 IKR, to photon momentum. We can diagonalize the system and ask what are the energies that the system gives us. The dispersion now looks like this. So instead of having a free particle parabola of our system, we have got a means here to change the dispersion of the system to go into a double-layer structure. And this is the spin-orbit coupled dispersion that we play with. This has been used in previous experiments to push the atoms over here and see negative mass effects. Or if you look at the excitation spectrum for BC that's sitting here, you see a photon-like minimum over here in the excitation spectrum. So this one is actually quite an interesting dispersion. And we have used this idea to create a unidirectional spin switch. And the idea is, again, we've got these 2 Raman beams, and the barrier is seeping through here now. But now we are living in a dispersion that's looking like this. And in addition, the spin composition of an atom along this dispersion changes. So over here, my spin is mostly spin up. And here I've gone to a mixture of spin up and spin down because the lasers couple spin up and spin down. And over here, I'm mostly in the spin down flip spin. So the question then is, what does a barrier do when you drive the barrier through the BEC? Here we've got spin up and spin down. This is the barrier running through. And you can see in this example, the barrier actually not only, well, the barrier flips atoms from the upspin to the downspin as it drives to the BEC. Okay, so there's a coupling between the spin and the motion of the barrier. And this is analysis. So let me just jump over here. How do you explain the action of the barrier on a BEC that's sitting still? First, you would say my barrier, I can actually decompose into all kinds of standing waves by Fourier decomposition. So a barrier offers you a certain spectrum of standing waves that you have available that's given by a Fourier transform over here. Then you say, what a barrier does is essentially a Bragg diffraction. So if you've got a matter wave running into a standing wave, it can Bragg diffract forward. So the incoming energy and the reflected energy is going to be the same. In our system, the atom is still and the barrier is moving. So therefore, this picture is true, but the atoms see Doppler shifted beams for the Raman loops. That Doppler shift depends on the velocity with which I move. So I pick up a phase factor over here that says the energy of the BEC is going to change because the Doppler shifted Raman beams are coming in. So absorption and emission are at different energies because of the Doppler shift. And therefore, in this process, the BEC also gets an energy. So one can then describe this process as a 4-photon transition. The barrier can shift the BEC along the dashed line over here. This is kind of having like two counter-propagating beams forming an optical lattice with a certain spacing. But then the barrier has got all kinds of frequencies in it. So you've got an assembly of these optical lattice that you can imagine to be there, followed by a Raman transition into the lower state. Okay, and then as the barrier pushes the atoms, this transition slides up here, and you ask, where do the atoms end up? There's two possibilities. They can end up over here, or they can end up over here. Once the barrier is gone, your atom needs to lie on the free particle dispersion, on the p² over 2m that I've shown over here. So these two components exist. I can argue why this one is not occupied. This has to do with going into the first frame or considering as an adiabatic rapid passage. Maybe I jump over this and just give you the essence of the spin flip that's coming out of this. So imagine you start out with the BEC over here, and then your piston drives through at a very slow speed. Okay. So what you see is that this is the energy momentum that you get from the barrier, and then you get the transition down into the other spin state. But if you look again, there is no crossing of this guy with the free dispersion parabola, which means your atom cannot undergo a spin state. It actually stays in its original state. If you move faster, then you're going to transfer the atoms from here over a 2-photon transition to this point. So you have undergone a spin flip. If you go really fast, the atoms don't respond to the barrier anymore because there is not a Fourier component in your omega that would be large enough to actually reflect the atoms. So you have to transform back into the moving barrier. You say, I've got a particle coming in that's really quickly now. If I don't have the Fourier component there to do a back reflection at that speed, nothing is going to happen. I can also go in the other way. And there's never going to be a crossing over here where I actually find a spin flip. So in this way, we have created a spin switch that is directionally dependent. That is unidirectional in the sense that if I go one way, I can flip from up to down, but not from down to up. This is what I've shown you here. If I would go the other way, I could flip from down to up, but not from up to down. And this is a new paradigm, I think, for spintronics devices. Okay, and I think I should probably end here. And thank you for your attention. And this is my group enjoying life in the ultra cold. Yeah.
When Thomas did his experiment with shock waves, we did a simulation of that. And actually, you observed some features which there is some similarity to what you see here. Because actually, when you have a fermionic system, you have a density wave, but then you have to look at what the pairing gap does.
Mm-hmm.
And the pairing gap does something very interesting. You see, when you generate the shock waves, it can go through pi and you form a domain wall, which propagates at a different speed. So actually, you have two types of waves. You have a density wave and you have a pairing wave. You see, gap wave. You see, which propagates. And you have actually many of those domain walls. You see, so in a way, it's like you have two fluids, somewhat similar to what you're having here.
Mm-hmm.
Basically, you couple two fluids together, and they propagate at different velocities. You have the density wave, which propagates at speed bigger than speed of sound. The other ones are slower.
Mm-hmm.
See, so I think there are some similarities in this
Mm-hmm.
between these two systems. They didn't see those experimentally because they didn't know how to measure, first of all.
Mm-hmm.
That.
Yeah.
You can do it, you see, but you have to measure the phase.
Okay. Mm-hmm.
Any other questions?
Yeah, I think that's an important question, and then it's also related to what we discussed before. So, in the classical theory of shock waves, let's take the compressible wave equation, which is pretty much like the GP wave. Of course, the GP has quantum density. But what actually happens is that the shock waves are explained by the theory of characteristics. So you have, because of their nonlinearity, the characteristics actually meet the point where the characteristic meet, you have practically singularity. The singularity is basically resolved by some dissipation, which actually leads to a different entropy. So there is a jump in the entropy of the system. And actually, this jump in the entropy is the reason why shock waves are also supersonic, because they're all related. So here in this problem that you have, I don't see any obvious dissipation in the system. Of course, my friend here said that maybe because we have a lot of vortices, this could be considered as a type of entropy. I disagree with that, because entropy is not related to the complexity of the system. Entropy is related to the loss of information. You can have a very complicated system, and still the entropy could be zero as long as you know everything about it. Entropy has to do with probabilities. Now, the GP equation describes a coherent state. So every vortex in this GP equation is by default entropy free. So my question to you is that if you really have a supersonic wave, if truly your wave is supersonic, first of all. And second, if it is supersonic, it is a proper soft wave, where is your dissipation? That's my question.
Sure. What you're looking at here is an effective 1D hydrodynamic model. And so you don't see the vortices, and so they turn into entropy. So in the 1D equations that are modeling this as a viscous shock wave, and that seem to work, there is entropy because this vortex tangle you don't resolve in the 1D scale. So the GPE itself has no dissipation. In the simulations, there's no dissipation, etc. It's exactly what you say, no entropy. But when you come down to an effective 1D model, now you see something that looks like there's viscous forces because of the formation of all this turbulence. And a similar thing happened, although not as complex, not with vortices, but a similar thing happened with John Thomas's experiment. They originally fit it with a 1D hydro model that said, oh, we have viscosity and stuff. But if you actually do the dynamics, now this is not vortex dynamics, but you just take into account the radial sides, right? So Slashnish and company did this. Then you get an effective 1D equation that looks like it has viscosity, even though it's completely dissipationless. So you get an effective entropy there because of whatever's happening in the other two dimensions. And that's why the equations look the same as something that you're expecting is coming from entropy, even though there's no entropy underneath.
That's right.
Okay.
Oh, yeah, that's fine.
There's one more.
And so to detect ring vortices, would you consider imaging along more than one axis simultaneously?
Yeah, this is what I think Brian Anderson did in the first vortex ring experiments. So they had solitons, they generated a soliton, they were able to make it snake, single soliton, and then they were taking images from the side, from one side and from the other side. And in both images, they would identify those that had single points and a faint light going through. Single points because you would look along the axis. You would integrate through a lot of nothing in the center of the vortex. And then a faint axis because you've got the tubes going down in front of behind the tube, but you still get a fluid in between. Absolutely. If you wanted to identify or to 100% certainly say that one feature that you have in there is the vortex ring, you would look from two different directions.
Answering your question. If you could.
Image those.
Yeah.
Mm-hmm.
Or you develop this technique to discuss where you kick out some atoms resonantly and try and measure the relative velocities.
Mm-hmm.
Okay, if there are no further questions, just thank the speaker.